In this next section, we'll look at the entropy at the molecular level. Basically, what we want to do is just fine-tune our understanding of entropy. We have this idea that it deals with the randomness or disorder of the system, but we really want to understand what allows this disorder in the system, what's happening in the molecular level. The other way that we look at entropy is in terms of the spreading out or the dispersion of energy. And the ways in which energy is associated with the position of the molecules and its distribution through the system. So again, what we'll try to do is come up with a more fine-tuned idea of what entropy is on the molecular level. All right, to give you an idea of the ways in which molecules can move, and so they can then utilize that energy, or how that energy might be spread out in terms of the motion of the molecules. We can have vibrations of the molecules. So as you see in the picture here, we have some water molecules that, where the bonds can stretch and get longer or shorter. The bonds can come closer together or get farther apart, as in the middle here. And you can have one bond stretch and the other one contract, as we have here. So those are all vibrational modes of energy. And then we also have rotational modes, in which molecules can spin on any axis in any direction. And then the third type of motion would be translational motion. And translational motion is the ability for the molecule to move from one place to another. So you could think of something in a solid state as having little to no translational motion, because they're locked in place. Molecules exhibit several types of motion. So right now, here the translational, we were just talking about the movement of the entire molecule from one place to another. Vibrational, which would be the periodic motion of atoms within a molecule. And rotational, the rotation of the molecule about an axis rotation, about some sigma, any one of the sigma bonds. All right, so these are different types of motions that you have available to the particles. Now, each thermodynamic state has a specific number of microstates. Now, here's where we get into quite a bit of kind of statistical analysis here. A microstate is any possible combination, position, motion that's available for the molecules. So you could think of a deck of cards as a type of analogy. There are numerous, if you were to look at the order of sequencing of the cards in the deck, there are numerous different possible sequences of orders that you could put the decks in a card. Each one of those would be called a microstate. That's somewhat of a simplistic example, dealing with just positions, but when you throw in different possible energies as well as positions, you come to realize that there's actually a huge number of microstates in most samples of matter. Boltzmann determined the relationship between the entropy and these number of microstates, and that's given to you in the equation here. And one of the things that this shows us is that entropy is an absolute value. It's the Boltzmann constant times the number of microstates that are available. So in general then, anything we do to increase the number of microstates available, whether they're modes of motion or different positions, any of those things that would increase the number of microstates would also increase the entropy of the system. The number of microstates, and therefore the entropy, tends to increase with increases in any of the following: temperature, volume, and the number of independently moving molecules. Looking at temperature, if you increase the temperature, as in our Boltzmann distribution graphs show here, the lowest temperature, 100 degrees, notice that the range of energies the allowable energies or velocities in this, in this graph, is more narrow. As you increase the temperature to the blue, we see that the range of velocities has increased. So we've allowed more microstates available for the molecules, and obviously if we go up to the green, we have an even greater range of velocities, so even more microstates. So in general, as you increase the temperature, you're going to have more microstates, which means that you're going to have a higher entropy for your sample. So that's kind of tick off our temperature there. Our volume, in terms of volume, if we increase our volume, we're creating more spaces, more positions for the molecules to occupy. And so again, that just simply doing that is going to increase the number of possible microstates. So any increase in volume of your sample, your system, is going to lead to an increase in the entropy. And then finally, the number of independently moving molecules will also increase the number of microstates. So putting things together, in other words, combining atoms with bonds, will lower the number of independently moving molecules. Breaking things apart will increase them. So any kind of breaking apart of molecules is going to increase the entropy. Also, you can imagine changes of state where you go from a solid to a liquid. Obviously, you have more moving molecules, in the liquid state than you do in the solid, and so you'll end up with, more randomness there as well. So it kind of takes care of that part of things.
We don't need no thought control. No dark sarcasms in the classroom. Teacher, leave them kids alone. It's just another brick in the wall.
It's common practice to look at, from a qualitative standpoint, the entropy and physical state. So you can imagine, obviously, in the solid state, which they have a picture here of water in the solid state is ice. And we know that the water molecules are fixed in position. Obviously, if you go from a solid to a liquid, you are going to increase the modes of motion, the distribution of the energy, and thus increase the entropy. And likewise, if you go from a liquid to a gas, you will also increase the degree of motion at which the particles can move, and obviously increasing the microstates. Solutions are kind of interesting, and we'll take a look at that in the next slide just to kind of analyze what's happening there. I mean, obviously, in a solution, you're dissolving for instance, in a solid, an ionic substance dissolving in water, you are increasing the randomness, the freedom of motion of the solid. But one thing you want to keep in mind is that although the ions, in this case potentially sodium chloride, although the ions are becoming less ordered, the water molecules are becoming more ordered. They have less microstates in the solution state than they did when they're randomly moving around. So you want to kind of keep in mind that in that process of dissolving, yes, you're increasing the disorder of the solute, in this case sodium chloride, but you're increasing the order of the water, the solvent. If we look at chemical changes, in general, for the most part, When gases are formed from liquids and solids, we will increase the entropy. So these are all things that cause increases in entropy. If liquid or solutions are formed from solids, so again, going from solid states to liquid states, if we increase the number of gas molecules that are increased. So if you look at the bottom one here, in the flask, this is a reaction between nitrogen monoxide and oxygen. So obviously on the left side, you have 3 moles of gas, and on the right, you only have 2. So this would represent a decrease in the number of moles, so it would be a decrease in the entropy of the system. And then finally, if you did anything where you increase the number of moles, if they were perhaps in the same state, so everything was in the liquid state, everything was in the gaseous state, if you increase the number of moles, you tend to increase the entropy. All right, finally, to wrap this up, we have our what's known as our third law of thermodynamics, which means that if you take all of the possible modes of energy out of a molecule, in other words, you basically remove all energy from it. So you have no vibration, no rotation, no translational energy, and you don't have the ability to swap particles apart, which means you have a pure substance. Now, when would you have that? Well, it's kind of given away up here, but at absolute zero, a substance would have no energy, and so you would have no rotation, no translation, no vibration. And if that also happened to be a perfect crystalline substance, so in other words, it were just one single particle, that you would have zero entropy. And again, what this does is it shows us that entropy, there would be only one microstate then, only the, in this situation here, each particle only has one microstate, and that would have an entropy of 0. So our third law of thermodynamics is that a perfect crystalline solid at absolute 0 would have 0 entropy. Okay, and again, that makes this an absolute scale. So any raise in the temperature other than that would cause the entropy to increase. Graphically, if we were to look at then a substance of solid, or substance, in terms of changing states, we see that we have starting at absolute 0, or there was 0 entropy, we would have some kind of an increase in entropy as the solid was heated, and then you would see a big jump when you go from a solid to a liquid. Obviously, the particles aren't being held in place nearly as much. You can now have more translational motion when you go to the liquid. Once everything's turned into a liquid, then again you have a rise in the entropy as you add more energy to it, and then you get another big jump in the entropy when you go from liquid to gas. Again, that huge increase in volume when you go from liquid to gas allows for many more microstates, and so the entropy goes up drastically there. And then if you continue to heat your gas, you get that same kind of increase in the entropy. In the next part, we'll take a look at the quantitative nature of this. So we'll start looking at some tables of entropy data and figuring out what the entropy change is for reactions and processes.